Biometrics predicting the duration of continuous speech tonal sounds. The article deals with the problem of division into sounds of continuous speech, determination of their parameters, and formation of basis of sounds characteristics of the voice of a particular person. It is proposed to build a distribution of lengths of tonal sounds and use it to predict the most probable length of the sound of continuous speech. The automation should more reliably classify sound fragments into tonal and noise. To do this, the automation must have information about the expected length of the sound in a particular speech of a particular person. The figure shows an example of an audio file with a tone-noise classification result. A study was made on the operation of the linear predictor algorithm for the classification of tone noise on several phrases of different people. With 10 repeated pronunciations shown in the figure, the algorithm produced several tone noise sections that are different from each other. The constant loss of sections of the length distorts the user's biometrics and affects the task of authenticating a person by voice. Figure 2 shows an example of the behavior of the autocorrelation function on a per-tone frame and an ill-conditioned one. Figure 3 shows a block diagram of the tone-noise classifier algorithm. The signal is processed on a linear predictor, gives an error and the value of the pitch period. Then the error passes to the threshold classifier and is entered into the noise database, on which the neural network tone noise corrector learns. The constant input of the signal contributes to the accumulation of the base, which gives a constant refinement of the thresholds due to the continuous training of the neural network. Figure 4 shows an approximation of the histogram by a mixture of 6 normal distribution laws for interval length values. This condition can be written by the following system of equations. Formula 1. The values of standard deviations of sound length distributions are approximately equal to Formula 2. Values P1, P2, Pn decrease monotonically. It is possible to estimate the probability of occurrence of each of the 6 normal laws by selecting equal intervals around mathematical explanations and counting the values that fall into these intervals. Calculations can be carried out once, because the ratios of the considered probabilities don't depend on the speaker, being the parameters of the language the speaker speaks. The superposition of normal distribution laws is presented in Formula 6. The essence of the ongoing research is to build the automation for calculating the average sound length and linking it to the tone noise classifier. The mutual work will be able to refine the parameters and accumulate the base as the signal arrives. An algorithm for constructing a statistical discrete continuum description of the duration of the sounds of the speaker's meaningful speech flow. It is shown that a qualitative tone-to-noise speech classifier should give output data 0 and 1, the duration of which is described by a continual discrete distribution of the values of the duration of intervals between sections of tonal sounds, distributed according to the normal laws. The discrete part of the distribution is formed by the discrete nature of the flow of appearance of tonal and noise sounds in speech, as well as their combinations, pairs, triples, quadruples, and others. The continuous part of the distribution of sound length values is due to the instability of speech when the pronunciation tempo changes. A method for calculating the average length of one sound of meaningful speech is given. The study made it possible to build an automation for determining the average sound length in different parts of the sound signal. The average sound duration is a statistical value and can vary when the speech rate changes. Therefore, after finding the multiplicity, the parameter is calculated. To determine the duration of possible combination of sounds, a continuous calculation of the parameter should be carried out according to the system. The figure shows an example of how synchronization works with ninefold pronunciation of the same phrase belonging to one speaker. The graph shows a signal that has passed through a narrow band filter and plotted straight lines that envelop this signal. The straight lines are obtained as a result of the tone-noise classification, a section where the deterministic part of the signal is detected are represented by 1, sections where noise is detected are represented by 0. Each sound fragment can contain several phonemes. The exact determination of the number of samples taken depends on the accuracy of determining the average length of the sound. The figure shows an example of the final process of phoneme synchronization in the processed voice phrase. When using the constructed sound phrase clustering algorithm, it became possible to synchronize and cluster parts of speech with the greatest accuracy. Taking into account the parameters described in the article, it was possible to build a neural network speech recognition technology based on the analysis both in the spectral and time domain of the parameters of a strict sequence of fragmented speech sections. For each fragmented section of speech, a neural network is built which generates a biological key for each phoneme, a vector made up of biological keys in the identifier for a particular person. The obtained study made it possible to build an automation for extracting the average sound length in different parts of sound signal. Also, in the article it is proved that the following equation is solved by an iterative method. Algorithm for constructing a sound fragment data of speech for recognition of voice images, taking into account the biometric features of the speaker. The paper proposes a method for identifying the personality of the speaker based on the results of the analysis of fragment of speech. A new method of speech fragmentation is general and individual phrases is proposed. The introduction of this method is of clustering sound files into the system of voice authentication of a person's identity made it possible to reduce the probability of error of the second kind, identifying an outsider as one's own, to a passphrase containing 3 words. An automation was built for the selection and classification of sound fragments of continuous speech. Let us describe the basis speech recognition system that underlies many algorithms. This system consists of the following steps: signal digitization, overlay window, primary processing of the frame, search for starting and ending points of phonemes and frames, analysis of the properties of the selected fragments, comparison of processing results with instances stored in the template library, issuance of results. In the primary processing of signals, the question of frequency of digitization arises. The human voice has a frequency range of 340-400 kHz. When processing frames, there is a need to normalize them in terms of amplitude, since the same phrase, uttered by the same speaker in different external conditions, is perceived differently. There are various ways to solve this problem. The most difficult is the fourth stage, finding the beginning and end of the frame. To isolate a single word in real time, many authors use the Rabini-Sambur endpoint determination method, based on calculating the frame energy and transition frequency of the function describing speech through zero. The frame energy is determined by Formula 1. After the beginning and end of the signal are selected, the next stage of recognition begins: the construction of the numerical characteristic of the frame. Here the method of calculating choke-capsular coefficients of calculating the coefficients of linear predictor can be used. After calculating the capsular coefficients of the linear predictor, a comparison is made with the library of standards and conclusion is made about the speaker identification. In this work, this model has been developed which makes it possible to authenticate the speaker at a noise level that exceeds the level of the useful signal. The first step in the recognition of an audio signal is the determination of vocalized areas of speech, that is, those areas in which sound signals are determined, which will be further analyzed. Before applying algorithms designed to recognize an audio signal, it is necessary to carry out clustering and determine the characteristic of the input signals, initial images on each frame. This is necessary to separate areas where noise is observed from areas where the signals are deterministic. To split the signal into frames, a narrowband filter with a given value of the fundamental tone is used in the work. Let us dwell on the issue of constructing a narrowband filter. Let's assume that you need to select a part of continuous signal, the spectrum of which part of the signal is enclosed in this segment. We denote the characteristic function of the segment as follows. The inverse transformation of the function is this. Let the fragment of speech be represented by the function. Let us denote the function by the spectrum. The band spectrum of function in a frequency domain has the form. By the convolution theorem, we have the expression. In the particular implementation of this formula, it is necessary to carry out a reduction and go to the next approximate formula. The value of t is chosen empirically. Let the sampling step, then the function is approximately calculated by formula. Subtracting the values, we arrive at the narrowband filter formula used in this work. For the most efficient splitting of the signal into frames, it is convenient to apply a narrowband filter, having previously chosen the initial approximation of the fundamental tone period. The difference between n is the value of fundamental tone period. In other words, the multiplicity of the frame on which the signal is analyzed. During the initial processing of the signal, the average value of the fundamental tone period is taken, calculated averaged over a database of 5,000 images. After the signal passes through the filter, it takes on a sinusoidal shape with a period. Sections where the signal doesn't have a sinusoidal shape are obviously noisy. Using this pre-procedure, it is possible to exclude signal section in which noise components and pauses are present, and it is also possible to determine the beginning and end of the audio signal. The amplitude of fundamental harmonic in Formula 6 is taken equal to unity. By changing this value, you can increase the amplitude of the sign of various phonemes. The accuracy of filter operation depends only on the correct choice of the value of the period of the main tone, t, which can be refined after obtaining the first vector of variation of the periods of the sinusoidal waveform according to Formula 6. To determine the boundaries of the signal, we calculate the power of output signals of the filter. It is known that the power of vocalized speech sounds of a signal increases when passing through a narrowband filter, while the power of noise and pauses drops sharply. Figure 2 shows an example of the operation of the function for calculating the power of output signals from a narrow band filter. In this work, the power is calculated by the formula. One of the main advantages of the filter is the good synchronization of output signals with the period of fundamental tone of the signal. Accordingly, it is possible to make a variation of the fundamental tone periods to refine the initial approximation of the filter itself by averaging the value of the variation. Knowing the length of the period, you can use the linear predictor filter to refine the determinism of the signal frames. We pass the image sound password through the filter 6. As a result, we obtain an almost periodical signal with a set of periods. Let us set and construct a filter with parameter. This algorithm shows to refine the value of the fundamental tone and thereby build a more accurate linear predictor. Below we consider a linear predictor with coefficients ak, which is defined as a linear system at the output of which we have to overcome the negative properties of computation processes associated with the poor conditionality of linear predictor matrices. Iterative methods are proposed in here. In linear systems, the parameters ak of a linear predictor are found by minimizing the error. The system of equation in a linear with respect to unknown coefficients, we introduce notation and write the system in the form. By applying the autocorrelation function on a frame that is a multiple of the sine period, the linear predictor filter will work more accurately than if it is applied to evenly spaced frames. So by checking each section, you can completely get rid of non-periodical signals by comparing the period of the sine with the period extracted from the linear predictor filter. Figure 3 shows an example of signal processing by the above procedure. As you can see, there are several different phonemes in the signal that describe the main biometric components. The next task is to recognize and classify the section of speech. After filtering signals, the sections that didn't pass the test of determinism can be turned to 0, the rest respectively to 1, thereby obtaining a tone noise classifier. Figure 4. Having accumulated a database of training images and performed signal processing, we have a vector set of phonemes. To start the recognition and classification of these images, it is necessary to scale the segments of phonemes to a constant length. The length is determined by the average pitch period, so that there are enough parameters to feed the neural network. When processing a male voice with a frequency of 44 kHz, sections are usually taken that are 3 periods long of the fundamental one. All sections are reduced to an equal scale for further correlation and neural network analysis. Having a set of recorded and processed phrases, we proceed to a comparative analysis, comparing the images one by one. Figure 5 shows a set of the first 20 phonemes of each image. Initially, the images with the highest correlation are selected. A correlation matrix with dimension kk is constructed. Formula 12. Pairwise comparison of scalable vectors allows you to determine the number of similar images for a given sample. If a correlation of 0.95 is reached among at least half of the images, the data is sent for training to a single layer neural network of the GOST R 52633 standard. where a check is made for matching images and a search for missing ones, those images that haven't passed the correlation analysis but actually belong to this classification. Correlation can be wrong in determining images, since the phoneme can be shifted in phase. At the identification stage, the Hamming distance is calculated to calculate whether the site belongs to this classification. The above procedure is repeated iteratively, decrementing the correlation in increments of 0.01 up to a value of 0.75. As a check, the VOC program displays pictures of phonemes for visual compression. The essence of the use of a correlation of neural network recognition lies in the invariance of the human voice. An important problem is the diversity of manifestations of the voice of the one person. The voice can change depending on the state of health, age, mood. This diversity presents seriously difficulties in isolating the distinctive properties of a person's voice. For example, figure 6 shows an example of the invariance of two phonemes. It can be seen from the figure that the phoneme in a word pronounced by the same speaker may differ, and each sample in the vector may vary with a certain amplitude. Neural network testing is used to recognize such invariance. After constructing a neural network sample, it is necessary to assign to each phoneme its sequence number in the sound signal in order to compose time intervals. The pattern of the phoneme can be repeated in different sections of the signal for some speakers, which is especially typical for the case of pronouncing the phrase in one breath. Figure 7 shows an example of the final clustering of sound phonemes. Each phoneme pattern has its own order or several orders at the authentication stage. For each phoneme, after clustering, a separate table of weights and a time interval is formed. During authentication, a similar noise reduction procedure is performed, only with the already known initial approximation of the narrowband filter. The introduction of this method of clustering sound files into the system of voice authentication of a person's identity made it possible to reduce the error of the second kind to 6 in -3 with a passphrase length of 3 words. Speech fragmenter for neural network biometric vocoder. In order to carry out the operations of identifying the speaker by the spoken password phrase, it is necessary first of all to convert a person's speech into a digital stream. This operation is performed by vocoders with the various implementation options. In speech elements vocoders, the spoken element of speech, for example a phoneme, are recognized during encoding, and only their numbers are fed to the encoder output. In such vocoders, automatic recognition of auditory patterns occurs, and not the determination of speech parameters, and accordingly all the individual characteristics of the speaker are lost. Modern vocoders are obviously not capable of solving high-dimensional problems. At present, when the restrictions on computing power have been removed, the linear algebra embedded in vocoders imposes its own limitations. In this regard, it is worth abandoning the old-style vocoders, which, due to the tightening of requirements for speaker identification system by voice, will soon cease to cope with the tasks assigned to them, and move on to the implementation of a new generation of vocoders, biometric vocoders, in which restrictions on the dimension of the solution being solved will be lifted task because At the moment, it is possible to train neural networks. Using biometric vocoders on neural network functionals, it will be possible to increase the dimension of the problem being solved until the result meets the set goals. Therefore, a base of biometric images for training should be formed. It should also be immediately taken into account that, along with the voiced phonemes, it should contain examples of all hissing sounds, since recent studies in this area have shown that the same hissing sounds reproduced by different people have significant spectral differences. Based on the foregoing, the problem of implementing a certain speech fragment data comes to the fore. First, the task of which is to organize the process of splitting a continuous speech signal into separate sounds or phonemes for the subsequent formation of a base of biometric images used in training biometric vocoders. Figure 1 shows an example of different options for fragmenting a given password. All of the experiments described below were conducted with two speakers, male and female, pronouncing 74 specific password words. The data was obtained at a sampling rate of 4000 Hz with a 8-bit ADC. Practice has shown that authentication is quite reliable of the length of a fixed voice phrase in 3 words of 4 or 9 letters, while training the machine will require about 20 examples of a given voice phrase. With an average word length of 7 letters, it turns out that for successful training of the artificial subconscious of a biometric vocoder, the speaker needs to pronounce a text of about 420 letters sounds, or about 2 lines of a text. It is important not only to implement the synchronization of each fragmentator frame with the beginning of the sound, but also with the middle of the sound. It is obvious that it is in the middle of the sound, especially voiced, that there are harmonics that most fully describe precisely the individual characteristic of the speaker's speech. The system must analyze the sound, and if it is announced, synchronize the fragmentator frame with the sample with the highest amplitude, because in most cases it is in the middle of the sound that the samples with maximum amplitude are present. If the sound is explosive, such as t, p, then it is obvious that the sample must be taken at the beginning of the sound, since based on figure 2. It is here that such sounds have harmonics that most fully describe precisely individual features of the speaker's speech. The precisely and advantage of this fragmentator is that it is low-level mechanism that will instantly learn on itself, simply by comparing the current sound with its neighbors, and at the same time creating a database of biometric images for their further use in training neural network biometric vocoders. Evaluation of the period of the main tone of speech, the selection of sound fragments during automatic learning of a neural network biometric vocoder. First of all, the system needs to determine how many sounds are contained in the incoming passphrase or free phrase input signal. To do this, you need to calculate the envelope of the amplitude of the speech signal. As a result, a function will be obtained, the graph of which describes the law of changes in time of the amplitude of the original signal. Accordingly, counting the jumps of extremes, the system will determine the approximate number of sounds contained in the signal. It is obvious that frame-by-frame processing of the speech signal will be used in this system, but the frames must be floating multiple of the period of the fundamental tone of the selected sound. The characteristics of the vocal tract can be considered unchanged over the interval of 10-20 milliseconds. Parameters must be measured with a frequency of about 50 Hz. Obviously, in order to determine the moment of the beginning of the next sound in a speech signal, the fragmentator must track the change in the pitch period in the signal. It should be noted here that, as a rule, the value of the period of the fundamental tone of a person is insignificant, but fluctuates with time. Its changes are usually within the range of 20%. Therefore, this interval must also be taken into account by the speech fragmentator. In order not to confuse the beginning of the next sound in the speech signal with the usual slight change in the pitch period of current sound. The same should be taken into account with selecting, comparing, and recording speech fragments in the database of images. Nonlinear algorithm for identifying periodicity. A digitized WAV file containing an 8 kHz speech signal and converted to an array is fed to the program input via a TXT file. In the future, it passes through a low-frequency filter without phrase distortions on 11 counts, the principle of operation of which was formed earlier. Splitting into frames, assigning each frame its own number, the beginning and end of the boundaries by samples and by time. The beginning of the main cycle of the program, taking into account the value of the period or lack thereof on the previous frame. Finding the maximum and minimum of the frame and determining zero relative to these values. Definition of positive and negative array according to the principle loop with step 1 from n1 to n2, where n1 and n2 are the beginning and the end of the frame. Shift of the positive array relative to the negative 1 by 2 counts. The shift coefficient is set in the program. According to the research results, it ranges from 2 to 3. Multiplying the resulting arrays to identify bits. Removal of adjacent strikes at a distance of 1 count by multiplying them. Comparison of adjacent strokes, adjacent through 1 and adjacent through 2, determining the maximum period of a given frame. Search for periods less than or equal to the period relative to the maximum with the value 10%. If the maximum period on the previous frame doesn't match the found one, procedures are repeated from 5 to 10. At 0 taken half of 1 up, at 0 taken 1 of half down. In case of failure to comply with paragraph 11, the repetition of all procedures in determining the maximum period in 3 cases of blows is considered. This procedure is necessary when changing the frequency of impact in explosive sounds. Figure 2. The presence of this predictor makes it possible to reduce the consumption of machine operation by several times, minimizing the number of variants of this algorithm. A digitized record of the phrase "Mom washed the frame" is given on Figure 3. When entering the frame number and pressing the button, we get all the proposed values. For visual comparison and verification of work, consider this section, Figure 4. We input the arrays of our strokes into some system like MATLAB, Figure 5 and 6. And visually on this frame there are 5 fundamental tone periods. As can be seen from the results, this frame belongs to explosive sounds and period is negligible, so the program went to check the zero change, figures 7 and 8. As you can see from the example, the last option turned out to be correct, so the program worked until the correct result was obtained among all entropies. Prediction of the duration of tonal sounds in Russian speech. This article was written in participation of International Mathematical Conference and summarizes the first article that was approved by the Higher Attestation Commission. Therefore, I will not dwell on it in detail, since it will be practically dubbing. The essence of the ongoing research is to build an automation for calculating the average sound length and linking it to the tone noise classifier. Their mutual work will be able to refine the parameters and accumulate the base as the signal arrives. A continuous discrete model of the distribution of the expected length of tonal sounds sequence in continuous speech. The following experiment was done, consisting in reading 15 lines of a Russian language text by one speaker. Next, the sound file was divided into tonal sound fragments. The histogram of the distribution of the duration intervals of tonal fragments of sound is shown in Figure 1. Figure 1 shows an approximation of the histogram by a mixture of 6 normal laws for the distribution of interval length values. Approximation is carried out based on visual perception. We see that the most probable value of the length of 1, 2, 3 sounds is multiple of each other. This confirms the theory described in the above articles. Therefore, I will not repeat myself and move on to the next article. Noise reduction in the processing of speech signals due to the selection of tonal fragments. The tone noise classification problem is the task of separating deterministic regions from those that don't have a periodic component. This slide shows an example of the ideal classification on a spoken phrase. A common algorithm for separating such a classification in the LPC, linear prediction codec algorithm. The algorithm involves dividing the signals into frames and further analyzing these areas. At the output, after analysis, the belonging of the site to either tone or noise is determined. As an analysis, an autocorrelation function is used, which by means of the obtaining coefficients filters the site to the type by which it becomes possible to determine its periodicity. Unfortunately, this approach doesn't reveal synchronization, that is, it doesn't show the beginning and end of the period, but only indicates its presence. The accuracy of constructing automation for fragmentation of sounds isn't satisfactory because of the probability of error of the classifier. The figure shows the section of the deterministic signal and the behavior of the autocorrelation function on it. The need to separate tone sounds arises when solving voice authentication problems, when building a database of biometric parameters. The task of separate classification means a clear and constant, when response in a phrase, determination of the beginning and end of the sound. As a solution to this problem, the following method is proposed. The method is based on the conversion of the original signal into a sinusoidal one. The original signal taken from the microphone and digitized at a high sampling rate, 32 kHz, will be considered as an example, as is fit to a sliding filter and in a single step. For reliability, the difference in the length of 3 periods is chosen, in order to avoid extraneous sounds that are not related to the speaker, as well as for monotony of the existing scenes. As an initial approximation of the period of the basic tone, an average value is selected, obtained as a result of counting all possible periods from the linear predictor algorithm. The figure shows an example of a signal filtered as a first stage. The meaning of the filter is to obtain a monotonous and continuous sign. The areas of the output signal on which such a requirement isn't met are noise. The period of the sinus coincides with the period of the main tone, from where it becomes possible to extract and refine it later. Accumulation and subsequent calculations of the tonal period are carried out on evenly divided areas for further repeated supply to the filter. The figure shows an example of the overlay of the output signal on the original with the periodic component highlighted. Areas of the output signal where the sign isn't monotonous are removed. Further analysis is performed in another space that contains only deterministic regions. Relying on certain beginnings and ends of the sound, similar sections of the original signals are cleaned accordingly. Having made a separation to solve the above problem, the X and Y signals are scaled to equal intervals in time. Extrapolation is carried out according to the found mathematical exceptions of the period on the main tone. Such fixation of the period allows you to reuse the algorithm of the linear predictor to eliminate and minimize the error. An example of a signal that has passed the entire algorithm described above is present in the figure. Ultimately, we have a signal isolated from the noise and interpolated at regular intervals of the length of the main tone, the meaning of which we also know. This situation makes it possible to create a database of tone sounds for subsequent transmission to a neural network for pattern recognition. By repronouncing the same phrase, the regions will retain their phrase and contribute to the training of the neural network. The figure clearly shows the synchronization of the phoneme after the pronunciation of the same phrase by the same speaker 20 times. The phoneme is represented by a length of 2 periods. As you can see from the figure, phrase distortion and erroneous capture are not observed, which makes the training of the neural network as stable as possible. The essence of the research is to build an automation of sound fragmentation for further accumulation of the base and solving the problem of voice authentication. The slide shows an example of the work of a neural network with synchronization by one phoneme. The difference in samples is represented by Hamming measure. In the future, it is possible to identify a large number of phonemes, which will give a larger number of biometric parameters and accordingly more reliable authentication. Creation of a modeling environment BioNeuroGolos focused on training large artificial neural networks by algorithm GOST R 52633 when performing laboratory from by Russian-speaking students of university in Russia, Belarus and Kazakhstan. Currently, the problem of obtaining reliable biometrical data by students of Russia, Belarus and Kazakhstan has been solved through the use of the modeling environment BioNeuroAutograph. The need to create this product is due to the fact that manufacturers of biometric tools don't provide free support for their products. It is because of the insignificant material costs of the modeling environment BioNeuroAutograph was in demand by universities in Russia. However, the only technology for analyzing handwritten biometric data cannot adequately reflect promising technologies in university courses. This becomes obvious due to the fact that neural networks are convenient for reproducing and supporting the effects of quantum superposition. That is, reliable biometric data in the near future will be demanded by universities not only through the departments informational security but also by the departments of computer engineering for laboratory work on the study of quantum computing. This is a need to create another modeling environment, BioNeuroGolos, focused on the use of a plug-in or built-in computer microphone or laryngophone. Presumably, the new simulation environment will be existing software models environment, bioneuroautograph, and differ in some additional functions. One of the differences between the new software product is that it is necessary to take into account the possible desynchronization of the fingers and voice of the user. To enter the voice image using the microphone, the user must press the record key, while not always the uses the press key before the passphrase is spoken. Figure 1 shows a situation where the user correctly clicked the voice input sound. Figure 2 shows a situation where the user pressed the speech recording key late, but the microphone started to arrive late. Figure 2 is missing the first tone sound compared to Figure 1, therefore the automatically allocated audio processing intervals is incorrect. The audio file generated for processing is much shorter than other files in the training sample. It is marked as erroneous, and the user must confirm the detected data entry error. The need for such additional functions is due to the fact that in the mode of operation of the modeling environment BioNeuroGolos, in the mode of the biometrics code converter, it is supposed to use a simplified algorithm for selecting a voice phrase at the beginning, the first of the tonal fragments discovered, at the end of the last of the tonal fragments discovered. A completely different situation arises when there is a splitting of the merged speech into sounds. Figure 5. In this case, each sound creates its own neural network. There are many neural networks, and all of them must form a system of output codes with high corrective power. At the same time, neighboring neural networks should correct each other, and the group corrective ability should be much higher than the corrective ability of a classical radiant codes, for example, BPH code.